This tutorial will demonstrate how to run Mega software from within the CASED simulation in order to align sequences and build phylogenetic trees. We will use one of the HIV cases to illustrate this, specifically the case of Lisa. This is actually Lisa's photo here. She's one of the cases for whom we have a video case scenario, a real person living with HIV. And to learn more about her case, we can click on Lisa, who's one of our US cases. And then you could read more about Lisa's case or view the video of her case scenario, but we're going to focus on the bioinformatics part of this case. And in this case, we're going to be comparing sequences from HIV isolated from Lisa with viruses isolated from the boy from whom she thinks she contracted the virus on a vacation. This person has a very highly pathogenic strain of HIV and progressed very quickly to AIDS, and we want to see if we can determine whether Lisa also has a highly pathogenic strain. So we'll start by opening up the software simulation. Click to continue. That takes us to the data screen. For now, I'm going to close the sequence analysis and the help windows. So what we want to do is open up some DNA sequences. So I'll click on DNA on the button bar and then browse in the CASED folder to the cases folder. And these are infectious disease cases, HIV, and this is a case set in the US. And we're going to look at the Lisa case. And in that case, there are files that can be used to analyze ELISAs and Western blots to test for viral loads, but we want the bioinformatics files. And all the files that begin with the word DNA are nucleotide sequence files, and they all represent HIV sequences from the various characters in this case scenario. I'm going to shift click to open them all at once, and now I'm holding my shift key down. I don't want to open the primers at this point, and then open. And now all of those sequences are open in the opened and processed window. Each of these sequences is an entire HIV genome, so they are about 10,000 nucleotides long. If we click on the first one in the list here, the boyfriend, in the main data screen window, then we can see that this sequence, it's about a little over 9,000 characters, and those would be 9,000 nucleotides. If we wanted to see the entire sequence down in the lower window of the main data screen, the size button is checked here, but if we click on the sequence button, then we can actually view the entire sequence of this file. Now, if we wanted to line these sequences up, 9 or 10,000 nucleotides is doable, but it would take a very long time. So what's typically done is to use PCR to amplify just a small portion of the sequence, and then that is what is used for sequence alignment. So in order to run PCR, we need some primers. We're going to go over here to the button bar and open a primers file. And now the forward and reverse primer sequences are showing in this main window here. And the primers are also indicated in the open and process window. So we can run PCR on all of these DNA files at once by shift clicking on the first file and then scrolling down to the last one, holding the shift key down and clicking on the last one so that they are all highlighted. And then right from this quick load run button, we can choose PCR and say run PCR. And in the open and processed window, which I'm going to make a little bit bigger, we see there are some new files indicated with PCR in parentheses after the name. That indicates that this is the PCR product of that reaction. And if we click on one of those, remember the boyfriend's DNA sequence for the entire HIV genome was a little over 9,000. Now the PCR product is only about 320 base pairs long. And again, we can view the sequence here in the main sequence window and see that it is much shorter than the original sequence. So what we want to do now is select all of the PCR products for sequence alignment and build a tree out of that alignment. So I'm going to highlight all of the PCR products, just the ones that have PCR at the end, clicking on the first one and then holding my Shift key down and clicking on the last one. And then this time we want to use the Analyze button. So we will click on that and select Align and Tree. And we're going to do this directly from the Open and Process window rather than send sequences to the export field, which we would want to do in other situations. And then we can choose to show just the tree or just the alignment or both. And let's choose both for this demonstration. So clicking on that option will activate the Mega software. A few new windows will have opened up. This is the main Mega window. That's actually not the one we're interested in viewing. That's how you would start from scratch with Mega. But what the KSET software has done is set up several steps to align the sequences and then build the tree from those sequences. So I'm actually going to move the main Mega window out of the way, and then we can see the tree window here and also the sequence alignment window. And if we look at the sequence alignment first, make this a little bit wider, we can see the 7 different DNA sequences that we chose for alignment. These are the PCR products from those different samples. It's just a small piece of the envelope gene, about 320 base pairs that were aligned. And then we have this color-coded representation of that sequence alignment. Each of the 4 bases is a different color. And we can see regions where the sequences are identical and then other regions where there are some differences. Plus nucleotides, you can see some regions of variation. And each of these sequences is compared in a pairwise fashion, and the number of differences between them will be displayed graphically as the tree. So let's take a look at the tree window, which is behind here. Make it a little bit bigger. And what we see is a branch tree representation of how similar these different sequences are to each other. The length of these horizontal lines is one measure of how many differences there are. So there are more differences between these 2 low pathogenic sequences than there are between these 2 high pathogenic sequences because these lines are shorter. And then the branch structure is also important because when we have a structure like this where these 2 sequences are on the same branch and they have a common branch point here, that means that they share some common ancestor in their evolutionary history. So by examining this tree, we can see that the sequences of Lisa and the boyfriend are very similar. They have very short horizontal lines, very few differences between them, and they're on the same branch structure. And then the 2 high pathogenic sequences are similar, very similar to each other. And then there's a relationship between Lisa's and her boyfriend sequence and the 2 high pathogenic sequences, indicating some commonality there relative to the low pathogenic samples that are present. So that does indicate that there is a good possibility that Lisa's HIV is more closely related to the high pathogenic sequences than the low pathogenic sequences. Now there are many other features of Mega that might be useful for your various analyses using these trees, and there is a lot of really good tutorial information about Mega itself on their website. A couple of features that I'd like to share. One is a way of changing the tree branching structure. What we're looking at is a traditional rectangular tree, and this implies an origin here on the left and a direction of evolution to the right. In this case, it's probably more accurate to use what's called here a radiation tree, and it's also sometimes called an unrooted tree. And in that case, you have no implied origin, it just shows the relationship between the sequences. So I'm making this a little bit bigger so that we can see everybody. So I don't think we'll be able to fit everything on this screen, but hopefully you can see that the sequences from Lisa's boyfriend and Lisa are more closely related. They have the shortest distance, the total line length going from one to the other. And if you measure the total line length going from Lisa to, say, one of the high pathogenic sequences, that's going to be a shorter line than going from Lisa to one of the low pathogenic sequences. So that indicates that her sequences are more closely related to the high pathogenic sequences. It's a slightly different relationship than what you see with the traditional rectangular branching, however. And again, you make that change by going up to this tree view button, and we'll go back to the rectangular tree. And if you want to save an image from the trees in Mega, you can use the image menu and say copy to clipboard, and then you can paste that into a Word document or a PowerPoint presentation or something like Paint where you can save it as a file. And then when you're done with the Mega components, the easiest way to close these windows out is to find the main Mega window, which is hiding back here. And closing this window will close all of the Mega windows, which is a lot faster than closing them individually. And I didn't point this out before, this yellow window that appeared when we first activated the Mega software. And this is just to indicate that it may take some time for those Mega windows to appear, depending on how many sequences you are analyzing and how long they are. So we'll just close that out, and then you can go on analyzing other aspects of the case.